came across. If it wasn't for bad luck, you know I wouldn't have no luck at all.
4.2 is on inductive reasoning, and if you remember from last day, we talked about inductive reasoning last day, so I'm not totally clear why they've done this in two sections in your book. We probably should have just done it in one, and in fact maybe I will do it in one when we actually do this. A reminder about inductive reasoning, it's when you're looking for patterns, and the one bit that I suppose is new today is they're focusing on in diagrams or figures. But basically, inductive reasoning is when you're looking at patterns and then you come to a conclusion based on those patterns. And remember, with inductive reasoning, it may or may not be true, your conclusion. So if it always rains on Thursdays for 6 Thursdays in a row, and then I think to myself, I notice a pattern, it always rains on Thursdays, and I think it's going to rain next Thursday, it's pretty, educated yes, but it only may or may not be true. Okay, a counterexample. We didn't talk about it last time. A counterexample is an example that shows that the statement is wrong. So for example, I've made the statement that it's going to rain every Thursday because it already has five Thursdays in a row, and then the next Thursday it doesn't rain. Well, that's a counterexample. Now it proves my statement was false. It only takes a single example to be a counterexample. So it's not like it doesn't have to rain for 6 Thursdays in a row until I've proven it. No, as soon as it doesn't rain once on a Thursday, I've proven that, or it's true that it doesn't always rain on a Thursday. So you only need to find one counterexample. So we're going to quickly look for some counterexamples here. Here's a statement, every prime number is odd. So, this is common when people learn about odd numbers. A number that can only be divided by 1 in itself. Numbers like 3 and 5 and 7 and 11 and 13 and 17 and 19. Often people say, hey, look at this, they're all odd numbers, so I think every prime number is odd. But that's not true. What's the counterexample? There's only one counterexample. 2. Alright, 2 is even and it's prime, so that's the counterexample to this one. Every month has at least 30 days in it. Well, it seems pretty good. They all have 30 or 31, so at least no, we all know that's not true because of February. That's the counter example to this statement right here. Multiplying leads to bigger numbers. 4 times 8 is 32, it got bigger. 2 times 10 is 20, it got bigger. Does this always happen? No, there's all sorts of things you could multiply that wouldn't make it bigger. What if you multiplied 5 by 0? That didn't get bigger, that got smaller. What if you multiply 5 by 1? That didn't get bigger, it stayed exactly the same. What if you multiply 5 by -2? That didn't get bigger, that got smaller, it went all the way down to negatives. What if you multiplied 5 by 1/2? That went to 2.5. Okay, there's all sorts of counterexamples to this one. Alright, we're going to predict the nth term in the following patterns. Why nth term? Well, last day we were saying like the 100th term or 40th term. Today we want to know the nth term. So it's like we're looking for an equation that we could plug any number we want into. So if we wanted to know the 100th term, we'd plug 100 into n. If we want to know the 40th term, we'd turn 40 into n. It's like a general term. So the way we can set this up is the same way I think I showed you last time. We have term number and we've got the value or the term itself. I think last time I did this vertically. I'll do it horizontally today. So term number, this is your n, okay? So we have our first term, our second term, our third term, our fourth term, our fifth term, etc. What is the first term? The first term is 2. The second term is 8. The third term is 14. The fourth term is 20. Let's start by seeing if you can figure out what the fifth term is. So as I said, we more or less did this last day. What you usually do when you do these questions is you look to see what's taking us from here to here. That's a +6. And from here to here, another +6. And from here to here, another +6. So from here to here, another +6. The fifth term is 26. Okay, great. But I don't want to know what the fifth term is, or the sixth term, or even the seventh, or the 100th. I want to know what the nth term is. So what I'm looking for is a formula using n. So I want to say that the value, like the number we're looking for, is equal to what? And last time I talked about this. If we're going adding 6 and adding 6 and adding 6, we're repeatedly adding 6. And repeated addition is the same as multiplication. So what you'd want to do is 6 times n. Now, does that work? Let's see. 6 times 1 is 6, but we want to get to 2. 6 times 2 is 12, but we want to get to 8. So what do you have to do? 6 times 1 is 6. What do you have to do to get to 2? Well, there's a couple of things you could do. You could divide by 3. You could subtract 4. Let's try the second one. 6 times 2 is 12. Divided by 3 gives you 4, so that doesn't work. But if you subtract 4, I think it'll work again. I think this is the formula. 6 times 1 is 6, take away 4 is 2. 6 times 2 is 12, take away 4 is 8. 6 times 3 is 18, take away 4 is 14. Yeah, this works. So this statement here, this expression, 6n minus 4, that's the nth term. If I wanted to know what the 100th term is, plug 100 in here. If I want to know what the 52nd term is, put 52 in where n is. 6 times 52 is 312, I think. Take away 4 is 308. Done. Okay, so it's very useful when you have a statement like this. You can find any term you want. Okay, let's do 2 more of those and we're finished this tiny little video. So we'll set up another one of these, term number and value. You don't have to do it this way, so it's just one way I find it's easier to do it, but you know, if you've got a different way, go for it. 1, 2, 3, 4, 5. First term is 3, second term is 6, 11, 18, and I'll try to figure out this term. So we went up by 3, went up by 5, went up by 7. Okay, I think you can probably see the pattern. What are you going to go up by here? 9, 3, 5, 7, 9, all the odd numbers there, right? So if you add 9 to 18, you get 27. That's your next number. Great, but we want to know the general thing, the general expression. How are we going to do that? Well, do you notice that even though it's not a common addition here, do you notice that if you go another layer down, it is? 3 to 5 is 2, 5 to 7 is 2, 7 to 9 is 2. If that's the case, it's often, but I don't think I can say always. I'm not 100% clear about this, but I don't think I can say always, but often, if you can get it to be the same on the second layer down, it means you're going to have an n squared as part of your formula. V equals n squared. So let's see if that works. If I put 1 into n, I get 1 squared is 1, but I have to get up to 3. So I could multiply by 3, or I could add 2. Let's see this one. If I squared this, 2 squared is 4, and again I could add 2. So this looks good. I think this is the formula. Let's try the next one. 3 squared is 9, plus 2 is 11. 4 squared is 16, plus 2 is 18. 5 squared is 25, plus 2 is 27. Okay, so not always, but often if you can get the repeated addition on the second layer down, you're going to have a squared term. Okay, here we go again. Term number and value. 1, 2, 3, 4, 5. The first number is 2, and then 6, and then 12, and then 20. We want to get the next number. So we go up by 4 here, we go up by 6 here, we go up by 8 here. Can probably figure out you go up by 10 here, so this number should be 30. To get the general term, well, again, we don't have the repeated addition here, but if we go one more, we do get repeated addition, which suggests that n squared might be part of the equation. So let's try. 1 squared is 1. We have to get up to 2. So you could add 1, or you could multiply by 2. Okay, 2 squared is 4, but we have to get up to 6. So you could add 2 to that. 3 squared is 9. We have to get to 12, so you could add 3 to that. Oh, and then you could add 4 to this one, right? 4 squared is 16 plus 4. So you're adding 2 to this one, 3 to this one, 4 to this one. Do you see that's just what the n value is? This one we added 1, n is 1. This one we added 2, n is 2, etc. So n squared doesn't get you to where you want to be. You have to also add on another n. So this will work. Now, some of you, because remember, there's lots of ways to answer these, some of you might have noticed there's another way you could get these numbers. And another way you could even figure out the answer is by looking at the answer we have here, the expression, and factoring. What's the greatest common factor here? N squared and n. Greatest common factor is n. Remember doing this last year? N times what equals n squared? N times n equals n squared. N times what equals n? N times 1. So this also works. This n times n plus 1. Now what does that mean, n times n plus 1? Well, this is my n value here. So if n is 1, then what's n plus 1? 2. 1 times 2 is 2. 2 times 3 is 6. 3 times 4 is 12. 4 times 5 is 20. 5 times 6 is 30. Cool, eh? I like this. Two quite different ways of thinking of the answer, but they both work. And that's a little bit of inductive reasoning for you.
Ow! You know, if it wasn't for bad love, I wouldn't have